In 1965, engineer Gordon Moore published in his own words a wild extrapolation, expecting the number of components per integrated circuit to double each year, which in turn meant that the price would halve each year. 10 years later, in 1975, he corrected his projection to a doubling of components every 2 years. To everyone's surprise, this is still true 50 years later, and has since long become Moore's law. However, the most quoted time frame over the years has been 18 months, which was actually a prediction by Moore's colleague David House. But let's do another wild extrapolation, back to 1965, the time of Gordon Moore's original statement and beyond integrated circuits, and compare this half a kilobyte core memory from about 1965 to this half a terabyte microSD card from about 2022. Usually CPUs are compared, but back in 1965 there were no CPUs. So let's use non-volatile memory. I'm aware that this will all be somewhat inaccurate, but fun nonetheless. Logarithms smooth things out quite a bit. While core memory seems ancient, its use as RAM while being non-volatile has its merits. The guy who would command the space shuttle's maiden flight was doing an EVA on the moon when he was informed that the shuttle project was greenlit. That was in 1972. So the space shuttle contained proven technology, which also meant core memory. So in 1986, after the explosion of the Space Shuttle Challenger, when they retrieved the wreckage, they could still do a core dump from the shuttle's core memory modules and recover data right up until the end. And, by the way, that's why a core dump is called a core dump. But first, let's explain how core memory works. Magnetic core memory consists of magnetic ferrite rings made of a ceramic material mixed with iron oxide and small amounts of additional metallic elements. Unlike ferromagnetic materials, ferrite is not electrically conductive but can still be magnetized. Magnetizing them one way represents a binary 1, the other way a binary 0. To address each core individually, we need to thread them onto a mesh of wires. The wires have a ceramic coating and are therefore insulated. If we now send only half the current necessary for flipping the magnetic field through each select wire, only the core where both wires meet will be affected. Each core acts like a transformer, just with less copper windings. That is where the name core memory originated, transformer cores. While writing is easy, reading isn't. To read a bit, we try to set it to 0. If it was set to 1 before, the flip to 0 will induce a current in a sense wire that is threaded through each core in a way that minimizes crosstalk. If the bit had been 0 all along, no current will be induced. The problem is that by observing the state, we may have destroyed it. Reading a bit that was set to 1 will always flip it to 0. So we need to write back the data once it was read. To do that, we need yet another wire that is threaded through all of the cores, called an inhibit wire. After a read, we set the inhibit wire to the opposite of the sense wire and flip the currents in the select wires in order to try and write a 1. If the bit had been 1 before the read operation, the inhibit wire will have no current and the bit will be set again. If the bit had been 0, the inhibit wire will carry a current and counteract one of the select wires, so that the resulting current is below the threshold of flipping a bit. You can understand now why there are so many wires. I can't imagine how difficult it must have been to thread them by hand under a microscope. It reminds me of the orphans that had to earn their stay at an orphanage by assembling the fusee chains for pocket watches in the 1600s and 1700s, the sweatshops of their time. Usually in core memory, the bytes, or rather words, were stored in the third dimension. By connecting the select wires of all layers, a word could be read in one step. Here is an example of such a core memory stack. It contains 19 layers, which implies the then common word size of 18 bits plus parity. Core memory got smaller as well. Here's an 80 kilobyte core memory module from the 1970s. 655,000 tiny ferrite rings. Each of the black squares holds 512 bytes, the same as our module from 1965, but with 4 times higher integration density. But back to numbers. I will not be adding freedom unit equivalents because this is all about proportions, which of course would be the same. The core memory has a capacity of about 0.0005 megabytes, while the microSD card has over 500,000 megabytes. The core memory has an area of about 171 square centimeters, and the microSD card has 1.65 square centimeters. The core memory's volume is 103 cubic centimeters. That of the microSD card is just 0.12 cubic centimeters. The price for the core memory was an inflation-adjusted 4,500 euros, while the microSD card costs only 50 euros. So for about 1% of the price, we get 1 billion times more memory. That is at the same time 1% of the area and roughly 0.1% of the volume. But those numbers are trivialities when it comes to integration density. While the core memory contains 0.000028 megabytes per square centimeter, the SD card has over 300,000 megabytes per square centimeter, which is 110 billion times denser. By volume, it's 0.000047 megabytes per cubic centimeter for the core memory and 4.5 million megabytes per cubic centimeter for the SD card. Almost 1 trillion times denser. Similarly, the price. An inflation-adjusted 9.5 million euros per megabyte of core memory compared to 0.000095 euros per megabyte of modern flash memory. 96 billion times cheaper. So 512 gigabytes of 1965's core memory would be 18.4 square kilometers in size. A square with sides of 4.3 kilometers, or over 110,000 cubic meters in size, a cube with sides of 48 meters. Try getting that for 50 euros. But let's see whether Moore's law is still valid, even though we left the domain of integrated circuits. We have 36.5 price halvings, 36.7 area halvings, and 39.8 volume halvings. That, over a period of 57 years, makes pretty much 18 months for every step, which is House's prediction and right down the middle of Moore's corridor of the original 12 months prediction and the updated 24 months. Nice.